rule keeping or what we call the rules for this seminars. This seminar is being recorded and it will be available to you after the presentation, so you can view it again. You will be kept mute during the web seminar. You can use question and answer windows to ask as many questions as possible during the presentation. Marcus will try to answer as many questions as possible at the time permits. Also, if you are on Twitter, you can tweet about this Keminar using hashtag Keminar from your account and also tag us at the rate Thieme Chemistry. I also request you to subscribe to our Chem series on the Cassini website so you can access to the all the previous Keminars that we have organized in this year so that you can have more knowledge with you. You can also subscribe to our newsletter to keep yourself updated about our papers that we are publishing, special issues and call for papers, and plus more seminars for 2025 that we have planned. So I'll welcome you all and I'd like you to introduce you to Thieme. Thieme is a 120 years old publisher, as we know, and we are basically published medicine and chemistry. We are here. I'm going to present to you the chemistry portfolio. We have journals, open access and subscription journals. We have something what we call a legacy journal, synthesis and synlet. Then we have our journals, open access journals, SynOpen, organic materials, sustainability and circularity now. Plus, we have a bioscience or what we call the journal, which has an interface between the chemistry and medicine, Planta Medica, pharmaceutical fronts. Then we also have a databases, science of synthesis and pharmaceutical substances. You can find more detail about our products on our website, themachemistry.com. So this year we have launched a new journal, Sustainability and Circularity, under the Professor Chris as a EIC. You can go through the content till now. 11 to 12 papers has been online on for these journals. Few more are in pipeline. You can go and read them. They are open access, free to read. And if you are working on sustainability and circularity, I request you to kindly submit your papers to sustainability and circularity now. And also, if for female researchers in our community, we have it's like a last date is just approaching. 13th is the last date for applying for Dr. Margaret Fuller Award in Chemistry and Women in Chemical Industry Award 2025. You can have more information on our website. If you feel that you are fulfilling or you know somebody who is fulfilling this conditions, you can nominate her. Still there is a time. We are open for a nomination till 13th December till 12 p.m. Please, if you know somebody very good female researcher, either in academic or working in the industry, please apply and nominate her. Here are the few call for papers in our different journals which are open. So if you are working in any of these areas, you are most welcome to submit the papers. We are looking forward for your submissions. And now I'd like you to introduce you to the today's speaker, Professor Marcus. Uh, he obtained his diploma in chemistry from Philipps University, Marlborough, Germany in 2007. He started his PhD with Professor Thieme at University of Cambridge. Here his focus is in development of continuous flow approaches towards the important organic transformation in selected natural products. Upon completing his PhD, he was awarded Pedro Leon postdoctoral fellowship by Alexander Humboldt Fellowship Foundation, allowing him to join the group of Professor Larry E. Overman at the University of California, Irvine. During his postdoctorate, he successfully synthesized alkaloids and terpene natural products as well as their analog, including their biological evaluations. In 2013, he returned to UK again for a postdoctoral position with Professor INR Bexell at the University of Durham, where he combined his interest of continuous flow technology and synthesis of bioactive target molecules. In 2017, he joined University of Dublin as assistant professor and he is promoted to associate professor in March 2023. Now I invite Professor Marcus for starting his talk. Thank you, Professor Marcus, for taking your time and sharing your research with us. Professor Marcus.
Okay, thank you very much, Rohit, for the kind introduction. And thank you also for the invitation to be part of this webinar, this Cheminar today. So it's my great pleasure to being able to share some of the work my research group here at University College Dublin has been doing over the last couple of years. And as pointed out, our research field is continuous flow chemistry. By background, we are organic chemists, so we're making molecules and developing routes towards interesting organic molecules, whereby we exploit flow reactor technology for various reasons, and I will mention why that is. As you can see from the title of the presentation, a focus of the seminar, the webinar will be on using photochemistry and specifically using photochemistry to generate reactive intermediates, whereby flow chemistry is the enabler for this. So in this talk, I won't go into great detail in terms of the underlying principles of flow chemistry. I will mention them briefly, but I will then try to use the time to showcase some recent applications from our lab. So I imagine most of the attendees are familiar with the concept of continuous flow chemistry, which essentially is a complementary tool to batch chemistry. Batch chemistry uses traditional glassware, round bottom flasks, and so on. In flow, the difference is simply that thin capillaries and microchips are used in order to continuously pump materials through different types of flow reactors. And there are a number of advantages associated with this. They're kind of summarized here on the left-hand side in this graphic, where reactions in flow are often faster and safer than batch reactions. That has to do with the better heat and mass transfer, allowing chemists to exploit flow technology for more challenging reactions, so where safety is a concern, or selectivity or reproducibility, and flow can help overcome these issues. Flow also has a positive impact in terms of product quality, which of course is very important for both academic and industrial applications. And specifically, this refers to product yield, stereoselectivity, but also purity, which is important again for industry if one can avoid extensive purification as downstream operations. And last but not least, flow reactors also are characterized by a smaller footprint compared to larger equipment that would be needed for scale up in industry. So what my research group and many others out in the community are using are commercial flow reactors like the one shown here on the right-hand side. So this is a system from Vaportech, which has the advantage of standardization. So anything we report, we publish, we report the exact detail, the exact components in terms of pumps, in terms of tubing, in terms of the reactor and configuration, and that increases the reproducibility. But flow chemistry, of course, can also be performed using home-built systems. So we just opt for these standardized commercial reactors because researchers in my group then can use them straight away. We modify them slightly if needed, but otherwise we can focus on the synthetic chemistry application. In terms of applications for flow chemistry, in the center here, I'm listing some typical applications where flow chemistry has found significant use over the last 10, almost 20 years, I would say, including metallation reactions such as lithiations, leading to a field known as flash chemistry, coined by the late Yoshida group. Using different gases, reactive gases, is beneficial in flow as well. So any reactions that are heterogeneous, if it's gas liquid or solid liquid systems, various reactions and reagents that are hazardous benefit from the miniaturized flow setup, the better mixing, the better heat transfer, the better safety, therefore. Photochemistry and electrochemistry are prime examples as well. And taken together, these fields of applications have led to the popularity of flow chemistry within the last decades. What my research group has, however, started to investigate more, and this presentation will show some applications of this, some examples, is the use of flow reactor technology as a tool for discovering new reactions and new reactivities, allowing us to explore chemical space, new chemical space through flow technology. So what I want to do in the talk is to share some case studies where photochemistry is used to generate reactive intermediates in flow, which provide new knowledge on new chemical reactions. But before doing that, I want to maybe just summarize, maybe for those in the audience that are less familiar with flow chemistry, the underlying ability and the possibility of applying flow chemistry to a variety of different types of chemistry, specifically thermal reactions, photochemical and biocatalyzed reactions. And here are simply three examples that illustrate that. The first one is about making this API, tecovirimat, which is the API used for the treatment of monkeypox. So it's the structure down here. And this can be made in continuous flow via two consecutive reactions. These are thermal processes starting from cycloheptatriene in the presence of maleimide at high temperature. It generates this scaffold, and in a subsequent thermal reaction with this acyl hydrazide, the final API structure is obtained. And what flow allows one to do here is to superheat the solvents. So in toluene at 145 degrees Celsius, we are above the boiling point at atmospheric pressure. Hence, we use a back pressure regulator. And the benefit of doing that is simply that the reactions are much faster. In 45 minutes, we perform the first step. And analogously, ethanol is used at 120 degrees Celsius in the second step. In 15 minutes, we can then complete the synthesis of this API. And therefore, within 1 hour, we generate the API exploiting flow chemistry. The second example here is a photochemical oxidation, which our group has been working on and recently published in collaboration with Almack and Corning. The method here oxidizes these benzylic positions to carbonyl products, ketones or aldehydes. It is a photochemical process where we use a water-soluble photocatalyst, which is this sodium anthraquinone sulfate species. We use compressed air, not pure oxygen, but compressed air, which is more attractive in terms of safety, but also more available. And then at slightly elevated pressure, we can reduce the reaction time to just below 60 seconds using UVA irradiation to affect this oxidation process. And again, this process is more efficient because of the intensification, the higher pressure, increasing the solubility of air in the solution, and also the irradiation of the solution with UVA light. And the Corning reactor plate that is shown here is very, very useful in order to enhance the mixing of such gas-liquid systems as demonstrated here. And the last example here is again from a collaboration with Almack a couple of years ago, where we combined high temperature rearrangement reactions, specifically a Curtius rearrangement in flow, with biocatalysis. And specifically what is happening here is that we convert this carboxylic acid via a Curtius rearrangement using this DPPA species as an azide source to an isocyanate at high temperature, 120 degrees Celsius. And then benzyl alcohol is used in order to generate the desired CBZ carbamate at the end. The problem here is that you have to use an excess of benzyl alcohol, as it is not very nucleophilic, so typically 5, maybe even 10 equivalents. And that is a problem because the boiling point of benzyl alcohol is very high, above 200 degrees. So therefore, its removal is more difficult because evaporation is not an option. So the solution we demonstrated here was to use an immobilized enzyme specifically CalB, this lipase species here, which would be able to derivatize the benzyl alcohol in the presence of vinyl butyrate that we pump in after the courteous rearrangement. And this derivatizes the excess of benzyl alcohol in this ester. And then via trituration, we can separate the desired product from the byproduct, in this case, on large scale, and therefore avoiding chromatography or more complicated purification strategies. So on this slide, hopefully what is illustrated and clear is that flow chemistry has different functions. One is to convert batch reactions to flow reactions that typically is associated with reactions that are not very efficient in batch, where there is a safety concern or a reproducibility concern. Process development follows onto that, and that leads to the optimization of a process, both in chemical yield, but also in space-time yield and productivity, which is, of course, very important for industry. And these three examples shown in this slide illustrate these 2 points, but there's an additional factor that is not illustrated in these specific examples, which is the discovery of new reactions and reactivity. And I would argue that this is an area which has been underexploited and underexplored in the context of flow chemistry, and that is why our research group here at UCD is quite interested in that. So moving forward, I want to share initially 2 families of projects where we exploited photochemical flow reactions to lead to the discovery of new reactions. And then subsequently, I want to share 2 more recent applications that just have been published. So the first one here is about benzyne chemistry, specifically benzyne chemistry, where the benzyne species as a very reactive intermediate is generated photochemically. And photochemistry has the advantage that reactions that are not feasible in the ground state can be facilitated in the excited state, whereby photons are used as tunable and traceless reagent equivalents, as well as an energy source. So specifically, what we have done here in the last few years is to focus on this building block here in the center of this slide, which is a carboxylic acid, a benzoic acid with this triazine moiety. And that is known since the 1970s to fragment upon exposure to UV light to give benzene, as well as CO2, nitrogen, and acetamide as byproducts. So this method is quite attractive on paper because the byproducts are very easy to separate. The reaction in batch typically takes very long, and that is problematic because it leads to over-irradiation and side reactions. But we did find that if we do this process in flow, we obtain the desired products in only 3 minutes. We use a high-intensity LED emitting at 365 nanometers, and then in the presence of a coupling partner that reacts with the benzyne, we get access to these interesting building blocks that are otherwise much more difficult to obtain. This building block, this benzoic acid itself, we found can be generated under analogous conditions, meaning photochemically, from this starting material, where a photochemical skeletal rearrangement takes place, which makes it attractive because this streamlines the excess of this benzyne precursor, and therefore allows us to explore this chemistry. What we found subsequently, and this is where discovery comes into place, were a couple serendipitous observations. For instance, that if we use secondary amines as coupling partners, we do not generate the benzyne species itself. We simply substitute this acetamide portion here, thereby generating these triazines. And these are underexplored scaffolds. However, they have some applications in medicinal chemistry, and typically one would require diazonium intermediates to access these species, which of course is not as attractive in terms of safety and scalability. And we also found that we can perform a similar intramolecular process where the amine component is part of this amide here, and that leads to a formation of a nitrogen-nitrogen single bond, as indicated, and the acetamide is again substituted, giving rise to these interesting benzotriazinone scaffolds, which again, they are known in literature, but they would require diazonium chemistry to generate these scaffolds effectively. So here, the specific examples with the triazine and the benzotriazinone, these are two examples of reactions that were not known before. They were discovered because of flow chemistry, where serendipity was helping in this process. A second family of reactions that follow a similar story concerns the photochemistry of isoxazoles. For the same reasons as outlined previously, so the ability to perform chemistry in the excited state, these isoxazoles are undergoing some interesting transformations. Some were known in the literature since the 1970s, but they were never exploited because the lack of selectivity and the lack of technology, even the lack of suitable light sources to perform this chemistry. And here, flow chemistry is the tool that allows researchers to do that. So specifically, what we did a couple of years ago was starting from these tri-substituted or even di-substituted isoxazoles. And here we use a medium pressure mercury lamp with a filter that blocks out undesired wavelengths. And upon exposing these isoxazoles, we were able to generate these oxazole products as rearranged photo products. And this is an interesting transformation, which is not obvious. It's not something you could achieve thermally, even with a catalyst. That would probably not happen. So photochemistry is quite unique in this context. As said, this reaction was known for some time. What was not known, and this is another discovery we came across, was what would happen when you use a regioisomeric starting material such as this isoxazole. So the only difference between these two is that we swap the positions of this methyl and this ester substituent, comparing these two and subjecting these isoxazoles to the same conditions. We did not get an oxazole product. We got something more interesting, and this is these ketinamine species, which are very reactive intermediates, very electrophilic species that can be used towards different heterocyclic targets. And typically, these would be very difficult to generate effectively in a single step via other means. So this discovery, therefore, was very interesting. Mechanistically, what we think is happening, and literature confirms that for the upper case, is that the UV light fragments the ON single bond homolytically, generating this biradical, which then rearranges to this acyl azarine. The azarine can undergo electrocyclic ring opening, generating this nitrilium species, and the enolate via its oxygen then performs a ring closure. That is how you obtain the oxazole. For the ketinamines, we start in a similar way. We also generate this biradical, but now if we rotate across this carbon-carbon single bond, we can position this methyl group here on the right-hand side, right next to the oxygen-centered radical, and a 1,5 hydrogen atom transfer is a unique step for this transformation that can take place. That also leads to a generation of an azarine as a reactive intermediate, and then the enol component can lead to opening of the azarine, back transfer of the hydrogen, and we generate the ketinamine. So this would not be a reaction you can design easily. So again, serendipity is important here to achieve this. And flow chemistry did enable us to do that. So moving forward away from benzynes and isoxazoles, which had various reactive intermediates involved that were generated photochemically, I want to move on to some more recent projects, specifically photochemical click reactions, and then some other interesting rearrangement processes. So photochemical click reactions, again, it's an area which is not new, but I would again argue it's underutilized in as much as the much more popular click reactions, sharpless click reactions to make triazoles and the likes are much more common. But you can also trigger click reactions using light, and classical examples are phyral-ene reactions, some diels-alder processes, and tetrazole-ene reactions. Specifically, we were interested in tetrazole-ene reactions because the tetrazole would liberate nitrogen gas that is otherwise difficult to handle, but in flow probably not so much, and it forms a reactive nitrile imine dipole. So flow chemistry can improve safety here, scalability, and provide control over these processes. So prior to our work, there was one report in the literature by Jameson who demonstrated that these aryl tetrazoles, when combined with activated acids, the carboxylic acids acted via DCI, would lead to acylation on the tetrazole, and then exposure to UV light in a homemade setup with a residence time for about 1 hour would fragment the tetrazole. You would lose nitrogen as a gaseous byproduct, and then the carbonyl of the former acid can cyclize into this position to give these oxidiosols. So it's a very interesting transformation, which of course is attractive in view of atom economy and the ability to change a tetrazole heterocycle to an oxidizole. Our own group built on this work. We used one of our Vapor-Tec photoreactors, which meant that we could reduce the residence time to only 10 minutes. And we used slightly different starting materials in terms of being a dye-substituted tetrazole, which upon exposure to UV light would again fragment these tetrazole to give the nitrile imine dipole, and that can then react in dipolar cycloaddition with these alkenes to give products of this type. And again, that's an effective and quick way to generate these species. More recently, a PhD student in my group, Davin, shown on the right-hand side here, took that work further, where specifically he was interested in making tetrazoles of this type, where the aryl group on the right-hand side would have a methyl substituent in proximity to the tetrazole. And these can be made quite effectively by combining these amidine species with diazonium salts in a oxidative cyclization. So just in one step, we can make these starting materials. And a first step then required the selective photochemical bromination of this benzylic position. So we use NBS and bromosuccinimide here as a brominating agent. Importantly, we use UVA light, 365 nanometers, and in only 10 minutes in the photochemical reactor setup, we can effect the selective monobromination in this benzylic position. At the bottom, you can see a number of examples where the bromine is introduced. And it's important to point out here that in this process, we were quite happy to see that it is selective for monobromination in batch. What is often a impurity is the dibrominated material, which is typically very difficult to remove. So here we can avoid that. And even if we have two methyl groups, we can selectively monobrominate one of the methyl groups, or if we use a little bit more NBS, we can selectively monobrominate each of the methyl groups, again, without dibromination. And the bromide here was required as a leaving group to then introduce this propargylic moiety that we would need subsequently for the photochemical click reaction. So here, essential is that the tetrazole is engaged in a photochemical bromination on this benzylic position, and we selectively use 365 nanometer light, which allows the bromination to take place without touching the tetrazole. So this is an example of a chromoselective reaction, which has advantages in terms of selectivity. So the subsequent step, which is the photochemical reaction, is shown here, where we found, as expected, that if we subject these substrates to our conditions, so that's again a mercury lamp with filter, we would fragment the tetrazole, we lose nitrogen here, and the alkyne is then clicked into its position, and that gives access to these interesting tricyclic heterocycles. The process is very efficient, so only 2 minutes are needed to generate these materials. And we again use a back pressure regulator to allow for the removal of the nitrogen gas byproduct. And the yields are generally quite good, quite high. If we use an alkyne, we get the pyrazole as the aromatic species. And if we use alkenes, we get the pyrazolines, which are a little bit less stable. Hence, the yields are a little bit lower. But depending on the length of the tether, we can get 7-membered rings, 8-membered rings, and so on. What is important maybe to stress here as well is that we do typically recover unreacted starting material. So in this example, 68% yield of the desired product and 13% recovered starting material. But I think that's not a problem because we can re-isolate the starting material and recycle this. And that is more effective in our experience than increasing the residence time to achieve full conversion of the starting material, but at the expense of decomposition of the product, which at the end of the day would lead to the same, if not a lower yield of the product. So this side here on the left-hand side, essentially, if we have ethers as tethers, we get the expected click products. So discovery is one of the themes of the talk, and this came into play when we used amines as tethers. So here a nitrogen LR-amine tether, because here we observe that we get a different product as the dominant product, which is this benzotriazepine scaffold. We get a small amount of the regular product, but the main product is this species here, which we proved by X-ray crystallography, and you can see that the LR group is still present. What we believe is happening here is simply that the nitrogen by its lone pair can intercept this nitrile imine, and cyclization takes place to give these structures. And as long as there's no alkene or alkyne present, we can achieve that in high yield and selectivity, as shown here, where different alkyl groups or esters or benzylic moieties are tolerated. And again, we isolate a small amount of starting material, which we can separate and reuse. Take-home message here again is that flow allowed us to discover this new access to these heterocycles. There's very few ways of making them, typically with a carbonyl in this position. So the scaffold as shown here is actually a novel heterocyclic entity, and the synthetic access was discovered using flow chemistry and recently published in this ORGLAD paper. So to move on to one final case study, which I think illustrates that further, we also have been working over the last couple of years on using these chalcone substrates bearing alkynes in the ortho position. And we had reported in 2021 and subsequently that under photochemical conditions in flow, where again we use 365 nanometer light, a complex rearrangement would take place that was unprecedented. So that's again a discovery in which the benzene ring shown here would be converted into this ring system where you have the cyclobutene, cyclopentene arrangement as part of this complex scaffold. And we're also able to tweak the conditions such that we could generate the cycloheptatriene as an intermediate, isolate that, prove the structure by X-ray crystallography, and demonstrate that it's an intermediate by subjecting it to the conditions as before, which generated the desired product. So this is an interesting discovery in its own right, and it is based on this R1 substituent here being either an aryl or alkyl group in order to generate these products. So more recently, Rory, a PhD student in my group, built on this work where he simply left out the substituent on the alkyne, meaning now we have a hydrogen substituent, and he discovered that under the same conditions, we generate these benzofluorine products. So what is interesting here is that under the same conditions, in this case, we do not lose this benzene ring. It is still present in the product, but we generate a new benzene ring as part of this photochemical cascade. And X-ray crystallography was again used to verify the structures. So in a way, it's interesting to note here that from essentially the same scaffold, we can generate either 4-membered rings, 5-membered rings, 6-membered rings, or 7-membered rings. So it's quite diverse, this chemistry. In terms of the scope, it works quite well. The yields are sometimes a little bit lower because the product itself is a very good chromophore, so it absorbs the light as well, meaning that secondary photoreactions can take place, but we minimize that by reducing the residence time to about 5 minutes. And that means that oftentimes we re-isolate some starting material, but we can recycle that. Given that the residence time is very short, we can scale this process easily to make gram quantities of these products in a matter of hours. In addition to that, we also were able to demonstrate that we can functionalize these products subsequently via bromination reactions, via alkylation reactions on the oxygen. Interestingly, when this oxygen was converted to this methyl ether, a aerobic oxidation was taking place, so that would give this ketone here, but both of these can be independently brominated para to the oxygen group or nitrated. So this allows versatility in terms of exploring this benzofluorene scaffold. Of course, the question is how are these products obtained, mechanistically speaking? And we did look into that by performing a number of control experiments where initially we just added tempo as a radical scavenger, as one would assume that radicals are involved in this process, and that was confirmed by accurate mass. When we performed the same reaction, not in regular methanol, but in deuterated methanol, we observed that the expected product was formed and no deuterium was incorporated in this structure. So that indicates that there's no proton shuffling involved via the deuterated solvent. When we incorporate, however, a deuterium atom in the substrate, for instance, on this alkyne here, we do observe that the deuterium is retained in the expected position because this grouping down here used to be the alkyne. So therefore, there's no removal of this hydrogen/deuterium taking place in the mechanism. And maybe most interestingly, when we fully deuterated this benzene ring, we observed that the deuterium, which is in this ortho position, migrates to this benzylic position. So it would have been in this position, and as the new carbon-carbon bond here is formed, the deuterium migrates to this benzylic position, which is very interesting. And this, in fact, allowed us to propose a mechanism, which is shown here on the right-hand side, where essentially we propose that upon irradiation, this alkene of the enone is converted to a diradical. This diradical is intercepted by the alkyne, giving this 5-membered ring with a benzylic radical and a vinylic radical. And we propose that rotation across this carbon-carbon single bond here is possible. And that means that the hydrogen shown here in blue on the ortho position can be transferred onto this benzylic position via a 1,5 hydrogen atom transfer, giving this intermediate here. And this is the key step that is in agreement with our deuteration studies. And subsequently, rotation is followed by formation of a carbon-carbon single bond, giving this tetracycle, which tautomerizes to the final product. So here we were able to use isotopic labeling to support a mechanism that explains the observed outcome, and therefore helps us in understanding this chemistry. So with that, I'd like to come to the end of this presentation, where hopefully I was able to show how flow chemistry can be used in combination with photochemistry to generate reactive intermediates and interesting products that are related to these intermediates. But maybe in addition to that, how flow chemistry can be used as a tool for the discovery of new reactions, new reactivities, and new chemical space. And if you're interested in that, especially the element of reaction discovery, I can recommend this feature article 2 of my postdocs, Jorge and Elenia, recently published in combination with Professor Steve Lay in chemical science, which lists the examples that are known, but also discusses the potential flow chemistry has in order to lead to further discoveries. So with that, I'd like to just finish by thanking my research group, current group members as well as past group members who have been driving this research and studying these examples. And I also like to thank our funders from industry, from different funding agencies for supporting our work financially. And last but not least, thank you for your attention, and I'd be very happy to answer questions you would have. Thank you very much.
Thank you, Marcus, for your nice presentation. We have two questions from the chat that I have picked up. So the first is there any possibility to observe different reactives uh, in flow and batch?
Um, I think if the conditions would be equivalent, you would not see different reactive intermediates, but using inline analysis in flow, you might be able to gain more information. And that is because in flow, the material is traveling through the reactor. So you have spatial separation of different stages in the flow process, meaning you could observe and analyze the reaction mixture and different reactive intermediates at different stages, meaning closer to the starting materials, closer to the product, or somewhere in between. And it is therefore spatially resolved in flow. So the analysis is much easier. You can perform inline analysis in batch, and that is done routinely, but in a round bottom flask or an equivalent vessel, you would observe all the different reactive intermediates at the same time, and that would make analysis very different. And I would think that if you can observe specific reactive intermediates in a time and space resolved manner, you can exploit their reactivity individually, and that might allow you to achieve selectivity by diverting these reactive intermediates into certain pathways. But that depends case by case, I would say.
Thank you. The another question is there possibility to control the dibromo impurity in photo flow condition using NBS?
Yes, I think that's what we tried to do. So we did it only in order to make the monobrominated material and deliberately avoiding the dibromination, because the dibrominated product is typically the undesired side product. Our focus, therefore, was on avoiding this dibrominated material. But equally, if you wanted to make the dibrominated material, you would be able to do that by simply increasing the amount of NBS and likely also increasing the residence time. So there could be merit in doing that, because these dibrominated materials, if you can generate them selectively, they are equivalents to aldehydes. So you could hydrolyze the dibrominated species to an aldehyde and use those subsequently. This method would not be very attractive in terms of atom economy, just introducing two bromides in order then to exchange them to oxygens. But you could do it. It was not our focus, our objective. So we haven't done it ourselves, but I don't see a problem doing that.
Okay, so another question is Professor Buckman, congratulations on very inspiring talk. Have you had any problem with the solubility of SAS? Is there is possible to use only water in the reaction? Is photochemical benzene precursor safe? Do you have any information about that?
Okay, so it's kind of two questions in a way. So in relation to SAS as the photocatalyst, so it is a ionic species, and that allowed us to deliberately use a water-based solvent system. I think it's water and acetonitrile. I don't remember the exact details, but it's published in the paper. So we need a small amount of an organic solvent to dissolve the starting material and the oxidized products. But water can then be used in order to solubilize the photocatalyst and also as a greener solvent. And with that, it would also allow for inline separation by extraction as a consequence. I think there are variations on this photocatalyst available that are less ionic or not ionic at all. So if for some reason you would want to avoid water as a solvent, you could do that. But here we felt it is a benefit in view of using a green solvent. And I think also the solubility of air is higher in a water-based solvent system than in a organic solvent. In relation to the second question, which I think was about benzene being formed and the safety in association with that, um, it's a very good question because benzene is incredibly reactive. It's very unstable. You can't isolate it. Uh, but for our reactions, I think that's not a problem because we trap the benzene species in situ, having the reaction partner mixed into the stock solution. So therefore, there's no benzene exiting the reactor anyway. Everything will have reacted at this point. And the advantage of flow chemistry in this context is that with a residence time as short as 3 minutes, we never build up a large amount of benzene anyway, and we generate the benzene and we consume it within these 3 minutes. So you could argue that the flow process for making benzene and exploiting these benzenes is actually safer compared to batch, and yet it is more scalable. 3 minutes reaction time and good yields translates into gram scale applications. It's an overlooked opportunity, this photochemical benzene method, compared to other methods. I think it has merit and value, and it should be used more often. So hopefully our work might serve as a contribution towards that.
Thank you. The next question is, have you tried to make standardized photocatalytic flow device? Does it have a possibility of industrial scaling up, or it can be combined with heterogeneous catalysis to achieve better catalysis and amplification?
Yeah. Again, good questions. So with the photoreactor we are using, this is a standardized reactor. It's a commercial system from WaferTech. So we do not modify the system as such because by keeping it as it is, it makes it much easier for others to reproduce our work for their own application. The only things we will do as part of our optimization is that we will exploit and apply different LED or otherwise different light sources. And the advantage of these systems is also that you can adjust the light intensity, so the wattage, meaning you can fine tune the conditions um, in order to achieve selective but also high yielding processes. So that makes it easier compared to home built systems. In terms of scalability, yes, people in industry use similar systems, but of course it depends what is defined as a scalable process. For us in academia, if we can make quantities of 1 or 2 grams per hour, that is already sufficient because it means we can make 10 or 20 grams of these products in a working day easily. In industry, you might want and you might need to make kilogram quantities. So for this, you would not use one of these WaferTech reactors, but there have been publications in relation to kilogram scale photochemical syntheses in flow over the last 3 years. So that just needs talking between chemists and chemical engineers who can then build these systems. And that would also allow you to design photochemical reactors that can handle solids such as slurries. We have done some work in that area recently. I haven't talked about it today, but for instance, you can use hybrid approaches between flow chemistry and photochemical CSTRs, continuous stir tank reactors. So there are opportunities to incorporate solids and insoluble materials, even for photochemistry, but this is an area which is still actively studied. So there's only a handful of applications at the moment, but there's no reason why that shouldn't be and couldn't be exploited further.
Another question is, Is any of these reaction taken further on scale, or if we wish to take photo flow reactions on a scale, any bottlenecks and suggestion? I
Yeah, so again, some of these reactions and some of these projects were done in collaboration with partners from industry, and we developed the chemistry specifically in a way that there is potential for further scalability. Again, as said before, it depends how much product one might want to make. If we are able to make 10 or 20 grams per day in industry with further process optimization and more powerful light sources, I think scalability to 100 grams or beyond wouldn't be impossible. But typically, the published examples that report photochemical reactions in flow on kilogram scale, there's only 3 or 4 examples I'm aware of, but they typically redesign the reactor setup in order to achieve that. There are additional challenges associated with that in terms of the intensity of the light, the type of lamp or light source, but also considerations in relation to the energy that is released, specifically the thermal energy. If you have a very high intensity lamp, it will generate a lot of heat, which needs to be taken into account. So we don't do that in our research group. We stop at 10, 20 grams, but then we hand that over to our industrial partners who can scale it beyond that.
Yeah. So there is another question. The new reactions which are discovered in flow chemistry, are they reproducible in batch steps?
That's a good question. I don't think I have a good answer for that because typically when we discover these reactions, specifically the ones shown here, they exploit photochemistry, and photochemistry is less efficient in batch. So we have so far not translated the photochemical reaction from flow back into batch. It would be possible, I think, but you would lose some of the advantages that you have just gained by doing it in flow, such as scalability and high photon flux. So, yes, you can do it, but you would have to re-optimize the process. And the residence times for some of the reactions I showed here in flow of 2, 3, 5 minutes, I think in a larger batch vessel, they would translate into 10, 20, 30 minutes at least. And the longer you irradiate your reaction mixture, the higher the chance of side reactions. So therefore, unless there's a good reason, I don't think translating it to batch would probably be necessary or worthwhile. But again, we haven't done it, so it's a little bit speculative. You can do it, but it depends case by case if it's going to be better or similar in outcome.
The next question is, what will be the purity of the product if it's carry out experiment using homogeneous catalysis?
If you would use a homogeneous catalyst, and I presume that would be a photocatalyst in this case, of course, the photocatalyst is in the reaction mixture, so you have to separate it afterwards. But I think there's no major implication in terms of the overall purity. It depends again what the photocatalyst is. It also depends if you could separate it in situ as part of a flow process. So this question might be related to the SAS in this benzylic oxidation we did. So I don't think there would be a negative impact on using a homogeneous photocatalyst other than you have to remove it. And of course, with photo redox catalysis, which is very powerful and very popular, it is often not just a photocatalyst you need to add. There's typically additional additives you need in order for the photochemistry and the photocatalyst to work effectively. And that makes the purification a little bit more challenging compared to some of the situations I described here, where no photocatalyst is needed, which of course means no purification and removal of the photocatalyst is needed.
So here the last question for today. Uh, how can flow chemistry employed for non-homogeneous reactions?
Okay, yeah. So most chemists who perform flow chemistry in their own labs would, of course, say that non-homogeneous reactions are more difficult. If it's a gas-liquid reaction, that is usually easier because there's no implication on solubility in the sense of reactive fouling or reactive clogging, which is different when using solids or insoluble particles. So homogeneous reactions in flow that are gas-liquid reactions, perfectly fine. You need a back pressure regulator to ensure that the gas dissolves easily in the liquid phase, but otherwise that is okay. The situation is different when using solids as starting materials or when generating solids, which could be the desired product precipitating or a byproduct or side product. Here, the problem is that the narrow channels are then likely to be blocked, and that is a problem with the flow process. There's a number of solutions to that. There's even review articles that have been published summarizing these, involving agitation, sonication, CSTR setups, but often you would have to adjust the solvent that you're using. You would have to adjust the concentration. So it is a little bit more difficult. Sometimes you can pack the solid species into a cartridge, into a packed bed reactor, and that avoids the problem. But it depends on the specific application. If it's a heterogeneous catalyst, immobilizing it in and placing it into a packed bed reactor is a great solution. But if it's a stoichiometric reagent, the lifetime of this cartridge is limited, and you have to replenish that eventually. So it's not a question that can be answered with a single answer right away, but there are solutions that have been developed and have been published in the literature, including reviews. So it's not impossible. It is just a little bit different and needs a little bit more attention when designing the process.
Thank you, Dr. Marcus. So thank you for your all the time for this great presentation and answering so many questions in such a detail. I thank all the participants for this Cheminar, and I thank you all again. So we can close this meeting. Thank you very much.